Okay, so it's 9 o'clock and it's a long program today, so let's try to get started. It's the last day of the official program of the NIPS conference. This afternoon we'll have symposia and then the workshops, they start. But it's a great pleasure for me this morning to welcome Vladimir Vapnik to give the final Ed Posner lecture of NIPS 2015. To those of you who may not know, Ed Posner was a co-founder of NIPS, and the Posner lecture is given by an inside NIPS member with long-standing contributions to our area. Nobody is more deserving than Vladimir. He came here first time in 1993, and so many of the things that we're working on today can be traced back to his original thinking and great insights. Just think kernel methods, margin theory, structural risk minimization. Vladimir not only has the great insights, he provides the proofs, he writes the books that becomes a Bible for our community. He has a very long list of honors, awards, and affiliations that speaks to this fact. Vladimir came to the US in 1990, I believe, and shortly after, in 91, I had the great honor of starting working with him together. We developed the support vector machine that, despite the great tsunami going through the community today with deep learning, still is a very powerful and effective learning algorithm. But as one of the people that have worked closely with Vladimir, I can speak to a quality of him that you also will discover this morning. His great enthusiasm for the field, his endless belief in that there are new learning paradigms out there to be discovered and great new learning algorithms. So without further ado, Vladimir, please welcome, and let's welcome Vladimir, and let's hear about intelligent methods of learning. Thank you.
Thank you, Karina, for introduction. And it is great to be here. And let me start my talk. This is the content of my talk. I would like today to say that there are three different learning mechanisms. And the first mechanism, I call it core mechanism. It's based on structural risk minimization, developed in 1965-75. And this mechanism guarantees that convergence of obtained rule to the best possible inset. The algorithms, good algorithms, which people use this, say neural network, support vector machine, even deep network, it is just a reflection of this core mechanism. And I will call this core mechanism brute force mechanism, because the only guarantees that with increasing number of observations, one will converge to the best possible one. But people realize that when we train our machine, it needs much more examples than human students. Why? And the answer is very simple, but we did not pay attention for a while for that. It is because a human student has a teacher, and machine does not have a teacher. So an accelerating mechanism is possible when you introduce intelligent generator, teacher, and I will talk about this like a second mechanism of learning. Lastly, there is very interesting and unexpected mechanism I call synergy mechanism for monotonic rules that transfer several monotonic rules into one more accurate rule. And from my point of view, the intelligent learning is a combination of three mechanisms: core mechanism, accelerating mechanism, and synergy mechanism. And let me start from the very beginning. In the end of 50s, Rosenblatt suggests his learning paradigm. Whatever suggests Rosenblatt was he transformed input vectors x into vector zeta, using some transformed training data, and then construct separating hyperplanes. And from this mechanism, it is a great mechanism because it contains idea of how to construct learning machine. And there are two generalizations for that. One is neural network, which actually, from mathematical point of view, construct piecewise linear functions. And another mechanism, it is support vector machines, which I will consider today. That mechanism comes from reproducing kernel Hilbert space, and I will talk about that. But before I will talk about all this stuff, let me make one remark. In the 60s, Eugen Winger wrote a great article called Unreasonable Effectiveness of Mathematics in Natural Science. He told that when physicists looking in equations, they suddenly see in equations essence of event. And it looks like mathematics knows something about reality. So when I will talk today, I will demonstrate that because of structure of Hilbert space is very rich, we can see unexpected effectiveness of mathematics in support vector machine, and I will show how this mechanism, new mechanism, can be understood just from support vector mechanism, and that's the way how they come to my attention. So, but let me start with very formal setting. So, given training set, you would like to minimize expected loss, and you would like to do it in some set of functions. You always need to say that I will do it in some set of functions and describe this set of functions. But you should say how you will do that. But let us consider the simplest way how to do that. Let, instead of expectation, minimize empirical loss. And the main question was why this works. Why, instead of expected loss, we can take empirical loss and when it's working. But before I will start to give you formal explanation, let me come to basic idea of information theory which comes from Shannon. Shannon have a very simple question. He asked how many questions allow answer yes or no. One has to ask query to find the desired object among n objects. And the answer is L, which equal log 2 over n. And he explained how to do that. You should split your objects into subsets and then ask query in which subset the object you would like to find. Query will tell you in 1 second. Then you remove subset where there are no objects, and you have twice less object, and you continuously divided objects, and after log n questions, you will find this one. And you cannot improve this. It is just to guarantee you need log n, or how he told log, it is log n bit information. But it is the same for pattern recognition. How many examples with answer query 0, 1, one has to see, to find among n indicator functions one desired? And the answer again, log n. Because suppose you can create some vector x who split your set of functions in two subsets. One subset say 1 on this x, and another subset answers 0 to this subset. You remove one of them, and you continue to do like in Shonen case, and you will have log n what you need to show. That is number of examples. But you would say it is very difficult, say, to split your function into subsets. So what if I will do? I will take randomly vectors x1, xl, generated according to some distribution measure, and again ask the question, how many question I should ask Curie to find the function. And the answer is log n over epsilon. It's constant time worth. And also where epsilon is epsilon closeness, describe epsilon closeness of your function to the desired one, and that is in statistical words is exact theorem. And this bound cannot be improved. But you can continue and say, oh, I don't have in my set of functions the function which perfectly separate my data. How many examples I need? Okay, the answer is log n over epsilon squared in the denominator. It's again constant time worth, but log n, you have still log n. But then you can say, oh, I have an infinite number of functions. How many data I need? And the answer again, you need instead of log n, you will have VC dimension of the set of functions, and I will show in a couple of slides that it is a simple generalization of finite number of observations, or finite number of functions for infinite set of functions, and you have VC dimension over epsilon if you have a set of functions, the desired one VC dimension over epsilon square if you don't have. And this again cannot be improved. And let me start about core mechanism about structural risk minimization. And that is related to VC theory. So you have training data, x1, y1, xl, yl, x from one space, y is 0, 1. And you would like to minimize expected loss, but you can minimize empirical loss, and you are still asking when it's possible and why it's possible. And this is four main theorem of VC theorem. The most important theorem is that for consistency of empirical risk minimization, it is necessary and sufficient uniform convergence of empirical loss to expected loss, uniform over all set of functions. In fact, if classical statistics study law of large number, it says that you need not just law of large number, but uniform law of large number. So uniform law of large number is necessary and sufficient, and then you should decide when you have uniform law of large numbers. So you're introducing VC dimension in case when you consider any probability measure, or VC entropy if you consider some probability measure which is fixed. And I will skip last theorem because I don't have enough time. And I will say a couple of words how generalize VC entropy and VC dimension, this log n, which we saw in Shannon case. So suppose I have infinite number of functions and I have a finite number of observations. My function is 0, 1 functions. So I can ask how many different separation I can do with my set of functions on this sequence. And the answer is so n different separation. So I cannot have more than 2 to the L different separation, but usually I have much less. So log of n is describe log n of Shannon. So for the VC dimension, you're introducing entropy over distribution function, or you're introducing maximal, then it works for any distribution function. So you construct VC dimension. But what is most important in VC theory, it is VC bound. So you can say that for any function is in your set of functions, simultaneously the following inequality is valid. You have empirical loss plus confidence interval, which depend on VC dimension over number of observations. But if you have in your set of functions the function which perfectly separate your data, then you don't have square root. You have this this bound with no square root, but empirical loss is 0. And both bounds are achievable. You cannot improve this, whatever you will do. So, but this bound allow us to introduce structural risk minimization, which is most important structure for constructing learning theory. So suppose I have, say, a set of functions with infinite VC dimension. I can create structure on this set of functions. So it is nested set of functions with VC dimension which is increasing. And then for any fixed structure, I have my bound, which is empirical loss plus some confidence interval, which confidence interval depends on the VC dimension of this subset of function. So I have this bound for any subset. But now, what I will do, I will use this bound to choose function. Actually, I have two terms. The second term is responsible for choosing appropriate capacity of the set of function, appropriate complexity of the set of function. Because I have a structure, I choose a structure of appropriate complexity. And the first term describes me empirical laws, so I can choose the best function in this subset of functions. But now the theorem says that if I will use structural risk minimization and choose my function, so sequence of choosing of this function will converge to the best function in closure of my of my set of functions with infinite VC dimension. That means that any function, any set of functions, if you will use and make a structure on this set of functions and use VC theory, you will choose the best possible set of functions. And that is brute force algorithm, which says that do structural risk minimization, fit your data, and you will have everything. So I would say that all algorithms which we use, they're good algorithms. They reflect structural risk minimization, including deep learning, including support vector machine, including everything. We can talk about details, how they doing structure, how they minimizing loss, but the general scheme is this, and that is brute force in my today terminology. But I will need some specific theorem, which says that suppose I will consider hyperplanes in some space, in zeta space. So let I consider hyperplane for which norm of coefficients bounded by delta. Then VC dimension will be related to this bound. VC dimension will be less than this bound plus 1. And realization of structural risk minimization, it is exactly support vector machine. I'm minimizing my functions, psi, which is non-zero slot function, subject to the constraint, it is second line of equation on the bottom, and under constraints that my coefficients less than delta, so belong to subset with fixed VC dimension. And then I will try to change my VC dimension, to increase my VC dimension according to structure, and I will converge to the best possible. And that is brute force algorithm which we're using now, and there are no other, even Bayesian is reflect this brute force algorithm. But I would like to say that people observed that when student learning, they do it better than we in our machine learning algorithm. Why? Because student has an intelligent teacher. And I will talk in this part about intelligent teacher, and intelligent teacher can do two things. It can control similarity between examples and can help to transfer knowledge from teacher to student. And that is the most important part in accelerating of learning process. That's I will talk about that. There is an article published about that. It is, you can find it in Jimmy L.R. for September. So, but let us come back to Shannon. Shannon says that if you would like to choose one function from n function, you need log n bit information. And the same, that means that if you will train our machine, we need at least log n examples to choose one function from among n functions. But if you would like to choose faster, using smaller number of examples, then we need that teacher give us more than 1 bit information for any example. So he gives us 1 bit information, which is y belong to 0, 1, that is 1 bit information, plus delta, something else, which I will call privileged information. So, and because we have more than 1 bit information, we can hope that we will do better than in brute force algorithm. And that is subject have to do that. So let me introduce formally what is the classical setting. Classical setting is given pairs, find a given set of function, one which minimize expected loss. Now, new setting, I call it loopy, learning using privileged information. Given triplets, X is like in classical SVM, classical machine learning. XY is privileged information which generate teacher along with Y, YI. So we have a triplets, and again, we would like to find the desired decision rule, but we would like to find this faster than we will do in the first setting. So let me give you an example on support vector machine. So suppose we have red and green, and we construct support vector machine in separable case. So the theorem says that the number of observation, the probability of error after looking on our training set has this bound with no square root. Now we have non-separable case. Then we introduce slack variables. We're trying to minimize our functional, which is omega squared plus sum of slack, subject to second constraint, which take into account slacks. And we have bound which have confidence interval with square root. Empirical loss plus square root. Why is so huge difference? Because difference between square root and no square root is huge. And the answer is very simple. In this case, we're trying to separate, to estimate n parameters of vector W using L examples, and examples will increase with increasing number. And in this case, we have to estimate n parameters for omega, for vector, of separating vector, and also L parameters of slacks. It does not matter that most of slacks will be equal to 0. You still need to estimate. And that is why we have square root from that. Good. If it's so, maybe we can fix the situation. Suppose we have some set of function, psi of x, which contain our slack function. And this set of function contain m parameters, m3 parameters. Then we, in situation when we have to estimate n plus m parameters, finite number of parameters, using L examples. Can we do faster with no square root? Sometimes we can. And this is key observation. I call it oracle SVM. Suppose that our teacher, as privileged information, gives us value of slacks. Then we can prove then in this situation, we minimize again omega square, subject to constraint y minus ri. This is 1 minus slack, because slack is given to us, and we have this bound with no square root. And this is example, so you have support vector, which is a red line, you have blue line, which is learning using privileged information with slack, and green line is Bayesian. Both converge to Bayesian solution, but with privileged information converge much faster. It's no square root, it is just, it is no square root. But of course, teacher cannot give us slacks. He don't know slacks. He can do something instead of that. He can give us, so say, correcting space, X star. That is some formal space. And set of function in this space. And slack will be some function from this set of function. And it will give us triplets. And during training procedure, we will do two things. We will estimate slack function, and we will estimate our decision function. Good. So let's do it in framework of SVM algorithm. What is SVM algorithm? SVM algorithm converge our training data XY in the data zeta y, where zeta is mapped in some mapped space vector, and then construct separating hyperplane in this space. So we know that we can do that, but if we will use kernel, Mercer kernel, we, instead of inner product in this space, can have a measure in kernel in this space. So this is standard support vector machine theory. So the decision function has a form 1, and to find coefficients of expansion, we have maximized the functional subject to constraint, and that is the last line. But up to now, I did not see contradiction in this equation, because actually we're using kernel in two different senses. In the first line, number 1, we're using kernel like source of expansion functions. We're fixing xy, and we have some function of expansion. And in the second, we're using kernel like similarity measure between two examples. They can contradict each other. And when we're choosing for support vector machine, we're committing some compromise for that. Can we fix it? Yeah, when we have a privileged information. What we can do, we can continue this algorithm. We can map our x vector in zeta vector as for support vector machines, and our x star vector in zeta star vector as in the same way, but it is different spaces. We have two different spaces. So we minimize the same functional, exactly the same, everything like in support vector machine, but instead of slack, we're writing expression of slack in this space. And we have the same constraint. If you will look carefully, you will see that it is exactly support vector machine, nothing new, just slack described in special form. And we have dual space solution, which is solution is the same like in support vector machine. It is expansion over first kernel, but when we consider coefficients of expansion, we have extra term, second extra term. It is correction of concept of similarity, which suggesting teacher for every example. So we can try now to do the best for selecting expansion function and do the best for similarity control by teacher, because teacher gives us something x star which can control our understanding of similarity between examples. So let me give you an example to understand what we're talking about. So the problem is given amino acid sequences try to, of protein, construct rule of classification of family of proteins. So this is picture of 3D structure, but as a privileged information which gives us teacher for training examples is 3D structure of molecules. You know what, when you have 3D structure, you have everything, you can perfectly do whatever you want, but not on sequences. So you have picture of 3D structure, and you have under picture of 3D structure sequences. And that's what you have. This is table which describe different families. It is, and the first row is, the first column is what support vector machine does. The last column, what does the same support vector machine on 3D structure. And the middle column is when we're correcting using this privileged information. We're constructing, still we're constructing decision rule for the sequences, but we take into account teacher explanation. So you can see that sometimes we're improving 3 times error, sometimes 10 times, but sometimes we cannot improve, like with red star cases, but it is fine, because you know that, say, diamond and graphite has the same element, carbon, and the only different in structure. So without knowing structure, you cannot separate them. Probably this is the case. But this is the most important part of teacher influence. It is no knowledge transfer. It's a little bit difficult to explain, but I will try. As soon as you will have triplets, you have 2 path recognition problems. One path recognition problem for space X, and another path recognition problem for privileged space, X star. So suppose that we have a rule for X stars, and teacher choose the explanation in the way to do the best possible job, and you can construct decision rule in the space X star. And suppose it is good decision rule. Then the question, so if you have your data and you have decision rule in the space X star, can you transfer knowledge of decision rule in X star into knowledge of decision rule in space X? Let me give you an example for you to understand what I'm talking about. Suppose we have a problem about, say, classification of biopsy. You're looking at the picture in pixel space, and you should say, is it cancer or non-cancer? But along this picture, you have description of pathologist who can write aggressive proliferation of cells of type A into cells of type B, or absence of any of dynamic, and so on. Since pixel space is universal space, you can do everything in pixel space. You can recognize cancer, non-cancer. You can recognize male or from female. But you have high-level language, which is specific language for the problem. VC dimension on this set of functions will be smaller than VC dimension. So you can construct better decision rule. And now the problem how to transfer this decision rule into initial space of picture. So in artificial intelligence, there is a concept of knowledge representation in some space. And that was introduced by Minsky in 50s. And it has 3 elements of knowledge representation. It's called fundamental element of knowledge in space X star. Main frames means fragments of knowledge in space X star. And structure of knowledge, combination of frames. So let us consider as main element of knowledge support vector machine. And that is great about support vector. You can see all 3 elements of knowledge in the solution of support vector machine. This is the formula of support vector machine. The function of expansion, where you fix support vector machine, it's reflect fundamental concept of knowledge. You have different functions. And you have expansion of this function. So let us choose as frame this function or this kernel function. So if you have k non-zero support vectors, so we have k frames, k element of knowledge. Suppose we can make an image of knowledge of frame, image of frame in space X star in the frame of in the space of X. Suppose this image is good, I will tell you how to construct this image. But then you have expansion. If it's very good, you have even the same coefficients. You just transfer everything from the high-level knowledge to the low-level knowledge. But how to make a frames? So we have how to make an image of frames. We have M frames. It's written first line. But I would like to have image like expectation of this frame I am given by teacher, X star given X. So for every X, teacher generate me privileged information X star. And I will take my expectation over that, and it will be my image. It's exactly what we want. But this is just regression problem. Regression in the very special setting. So I have pairs x1, zeta 1, k. K means that I trying to reconstruct frame number k. And I have L observations. So I can construct one by one all these frames from the same data. You would ask me, what is the good? Why not transfer the whole function in this function? My answer is following. So here you're transferring only part of knowledge, not whole knowledge, only frame. And that requires less examples. That requires smaller VC dimension, and you can do it more accurately. So you transform frame by frame in the space, and then you do something. So how it works. And there's an intelligent algorithm. Why I call it intelligent algorithm? Because you have intelligent agent, which gives you additional information about problem, X star, given X. So you have intelligent engine, and you can use this intelligent engine. If I will have a time, I will talk especially about this intelligent engine. But how it works? So using just SVM, find classification in X star space, in high-level space. So then using regression SVM, construct transformation, construct images. I can say that images, it can be considered as features in X space. I transform X space. Now I have not X, but X, which is transformation of X space using knowledge of high level. Then I have a scores from the high level solution. So now my training triplets is completely different from whatever I had before. I have, instead of X, transform X. I have X star privileged information, which gave me features the same. But instead of Y, I have score. So I can solve this problem in the space X. And that is how it works. This is a problem which we solve for military guys. We use SVM, but it is problem about drones. The drones should fly fast among some territory and have a wide-angle camera and make a picture and then try to find in these pictures something which they're interested in. That is the problem. That is X space, when your drone flying fast and have wide-angle camera. But you have privileged information. With this drone flying on the same territory but slowly, and have a very good camera with high resolution but not wide, and flying back and forth. So when you will use information from real cameras with wide angle, you will have blue, that is error rate. When you use information which is whatever you use in slow flying drone, you will have green. But if you will transform your knowledge from one space to another space, you will have red. It is for different type of, different training sets. So, and that is the most mysterious way for training. I call it synergy of several decision rules. But it works only for monotonic decision rules. I will tell you what is that. So we can use, say, several SVM outputs of several SVM to construct new SVM, which we would like to be better than any of them. So, but to explain what is synergy, I should go back to structure of statistics. What is statistic about? The basic concept of statistics is cumulative distribution function. And that is what is that, cumulative distribution function. And the problem of statistics is the following. Given data, X and Y, defined according to cumulative distribution function, you should estimate a known cumulative distribution function, then density function, which is derivative from cumulative distribution function, then conditional density function, people interested in that, then regression function, then, but we will talk about conditional probability function. In pattern recognition, that's what we're interested in. But the only problem which can be solved from that and can have a good solution is estimating of cumulative distribution function. We have empirical estimate of cumulative distribution function. We have Blivenko-Contelli theorem, which says that it converges to real distribution function. And also we have a bound for that. And this is bound pretty good. It's exponentially fast and so on. But we don't have density because it is derivative. We cannot take derivative. It is ill-post problem. We cannot take conditional density function. It's ratio of two densities, even with known densities. So, let me go. Let's talk about conditional probability function, which we're interested in. That's what is conditional probability function. It is ratio of two functions. I have a numerator, denominator. Given data, I have to estimate that. I can rewrite definition in the way of this integral equation, this integral. And then I can say, okay, to estimate conditional distribution function, I need to solve this integral equation in situation when cumulative distribution functions are known, but I am given density, I am given data. So when you're solving ill-post problem, you know that the most dangerous part is small, is not. Suppose we have a solution, F0 is solution of this integral equation. Then we add, say, sign. If you will add sign, then and integrate, then on the right-hand side, we will have very small, small term which make a difference on the right-hand side. But solution is very different. And this is, say, what is difficult in ill-post problems. You have oscillation solution. That's what you need to do. But when you consider, say, solution in monotonic set of functions, you don't have oscillation. And we can prove that in this case, you have not ill-post, but well-post problem. So let's talk about support vector machine. In 1998, John Platt observed that support vector machine forms monotonic rules. Suppose that his observation is correct. Then we suppose we have several monotonic rules which solve the same pattern recognition problem. And I would like to estimate conditional probability, that probability of class 1 given scores for all these rules. And that is the best what I can do. It is God's solution. And this solution is not ill-post. It is well-post. And we can solve this. I should say that monotonic solution appeared in classical statistics, say, in regression problem. And it's called isotonic regression. But we was able to solve this integral equation instead of monotonic function. So now let me explain difference between ensemble learning and synergy learning. Ensemble learning is combination of several rules. But synergy learning is just synergy for monotonic rules. We're using that we can perfectly solve integral equations for monotonic rules. So monotonicity plays a role in that. So let me give you an example. That is different type of synergy. We take from UCA data, the data which has a lot of observations because we need to estimate well. And we consider two support vector machines. Support vector machine for spline and support vector machine where kernel is RBF. And you can see that, say, for one problem, 27, 47, 27, 20, and so on. And the last line is synergy of these two rules. And you can see that in every single case, synergy is much better than just. And say only the first column described something is not dramatically better, but the rest it's 15% better and so on for nothing, for just using two kernels. And that is geometry, how it working. So we took two support vector machines. One separated horizontal line, another is vertical line. And they have 20 about solution. But when you construct your solution and trying to construct synergy rule, it is black curve. It comes from concept of that. So now the most important, very important, how to solve multi-class classification problem. People solving multi-class classification problem like heuristic, let us consider one versus the rest rule. So you have one function constructed in one way. So the first class versus the rest, the second class versus the rest, and then choose the maximal score, which is wrong, because you're comparing apple and oranges to different solutions. But what you would like to compare, probability of class given one under all these scores. And you can see that it is huge difference for four-class classification problem from that. So, and then appeared the idea, how much cost synergy? So we took it for adults. We know that SVM gives, say, problem which converges to the best possible, to Bayesian problem. So we have 300 observations, and synergy gives 70.8% of training error. Then we increase for one kernel, for another kernel, of 1,000, 3,000. We did it even for 5,000. We did not reach this level. The question is, are we really need big data? Or we need smart to use small amount of data? I don't know answer on that. But here, I see that even increasing 10 times training data, you cannot achieve a result which gives you synergy due to monotonicity property. So I gave you three different mechanisms for learning. Core mechanism, all of us using that. But to get better mechanism, you need to introduce intelligent agent. You need to introduce new information. And synergy mechanism. So the only one remark I would like to say. So when I looking on accelerating mechanism, every time I'm thinking about that, I see the same pattern in many philosophies, starting from Plato. What Plato says, that there are two levels of knowledge. One level, it is level of ideas. And another level, it is level of things. Everything is coming on the level of ideas, and then you transform on the level of things. Kant repeats the same. And all German philosophy is based on this idea on two levels, of level of ideas and level of things. When you're trying to introduce, say, teacher, you're trying to introduce level of ideas. Because for this example, where I gave this breast cancer, this biopsy, what teacher described? Teacher describes the mechanism of cancer, the bad cancer eating, bad cells eating good cells. And he described picture in this term, in terms of essence, in terms of what's going on. But when you would like to recognize, you don't use this intelligent mechanism. You don't use this knowledge. You do not use high level of knowledge. You use just picture. And the theory, core theory, says you can do that, but you need a lot of data for that. But as soon as you introduce something smart, something intelligent, something which go in the essence of the problem, you can reduce drastically number of examples, and that's why students with teacher is better than just students. But mostly I finished.
Thank you very much. Thank you very much. I think we have time for just a single question, maybe. 2 questions, I'm told. So there are microphones around the corner. Any? That would be surprising. There's no questions. Well, then while Vladimir, can you please tell me, you had a table before. Why wasn't it filled out, that about the monotonic with the 1,000 and the 3,000 examples? Yeah. You have not filled that one out yet, or what is going to happen?
No, we have up to 20,000. We have up to 20,000 examples, but it is a recent experiment. We have 5,000, and it is not in this slide, but it also under not reach 15. We even have a synergy of 3 SVM, and we reach not 70.8, but 70.4.
Okay.
So, if I understand completely what means accelerating mechanism, it's 2 level. I don't understand synergy mechanism, not in terms of mass. I understand perfectly mass, but what it means for human being. The only what I can say, what I see, what I understand, and when I prepare myself to exam, I like to read 2 books simultaneously. The written is the same, but it gives sort of synergy. And also it is good to learn from too many teachers, not from one teacher. They mostly talking the same, but it gives synergy. But I forgot to mention here that this row, third before last, gives correlation.
Yes.
And correlation, it is very high.
Of course.
Over 95%. What it means, the most in different rule is trivial. But there is something very small amount, which non-trivial, and that is important. And also when you're looking on the picture, how you can understand what is that? Why this black is better than this is standard way what people combining a couple of rules. It does nothing. But synergy comes from mathematics, but I don't understand on explanation of humans what is that. I tried to talk to psychologists. I came to Princeton University to psychology department and tried to ask them, what do you know about, say, accelerating, about human? They say that we know nothing about that. But our great teacher taught us exactly in this way. So my guess is that machine learning, it's not about machine. It's also about human. But I don't understand human part in accelerating mechanism. I understand machine.
Thank you very much. I'm hoping that this can be the element that makes us again outperform the deep learning if we have multiple of these monotone.
Deep learning is brute force learning.
Okay. All right.
No. Let me explain why. I don't want to sell guys. Because what they use, what they use in deep learning, they minimize some functional, right? Which is structural risk minimization. They create structure, so this initialized weight. It is in structural risk minimization. They punished weights, and that is in Bartlett article about, you remember one of the first article about neural net, that weight is more important than the number of neurons. So there are nothing which was not in the scheme of structural risk minimization. The intelligence does not come from your invention, from technical. Intelligence comes from teacher. I don't know how teacher. But let me give you an example which I like very much. My friend studied how to play golf. And his coach explained me, don't hit the ball, seduce the ball. And every time when he hits the ball, you're doing like macho, you will not be successful in that, or in another way, you don't know what you're doing, it also doesn't work. And he told me that in a couple of days, he starts to understand what he should do. So this is perfectly describing on two levels, on level of essence and level of, and when I'm talking about intelligent, I'm talking about this. I don't know how this great coach invents these images. But that is what about intelligence. Not about math, not about computers, it's just stupid machine.
Okay. So now we might have, no, okay, now I'm sorry. I used up all the time for the questions. So let's thank you, Vladimir, again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.